Thank you for joining today. My name is Shannon Reed. I am the director of the Electrochemical Society, director of community engagement for the Electrochemical Society, and I'd like to welcome you to today's webinar, the Pacific Northwest Hydrogen Workshop. Before we get started, I want to go over a few items so you know how to participate in today's event. You may have joined the presentation using your computer speaker system by default. If you would prefer to join over the telephone, please select phone call in the audio pane and dial-in information should be displayed. You'll have the opportunity to submit text questions to today's presenter by typing your questions into the Q&A box of the Zoom control panel. You may send in your questions at any time during the presentation. We will collect the questions and do our best to respond to them during the Q&A session throughout the presentation. To begin today, I'd like to thank the ECS Pacific Northwest Section and those organizing the Pacific Northwest Hydrogen Workshop. Your hard work make today's webinar possible, and we look forward to hearing your perspectives and vision about hydrogen technologies and deployment, R&D needs, hydrogen's roles in decarbonization, and much more throughout today's workshop. And again, big thank you to Yuyan for putting this together as the organizer. If you are interested in getting involved in the Pacific Northwest section, or perhaps a ECS section in your region, feel free to reach out to us at customerservice@electrochem.org, and we will make sure to get you connected and involved. We'd also like you to mark your calendars. The 242nd ECS meeting is taking place in Atlanta, Georgia from October 9th through the 13th. Registration is now open and early registration ends September 12th, 2022. We also have a late abstract submission deadline coming up of September 23rd. So if you didn't have a chance to submit your abstract for the meeting during our first round of abstract submission, take a chance and submit your abstract before the 23rd deadline. We hope to see you at a future ECS meeting. And if you'd like to learn more about ECS meetings, visit electrochem.org/meetings. We do have an outstanding panel today and moderators. Again, I'd like to thank Yuyan Shao, who's the Chief Scientist at Pacific Northwest National Lab, for organizing today's event. And I know that we'll go through some more formal introductions once we get the presentation started. And so just as a reminder, benefits of attending today, we hope that the audience takes away information about roles of hydrogen and hydrogen technologies and decarbonization of our society, the status of industrial deployment of hydrogen technologies like fuel cells and electrolyzers, and the R&D needs and workforce development for hydrogen technologies. And so with that, I'd like to turn the presentation over to Yuyan at PNNL. Yuyan, feel free to take it away.
Sorry, I was muted. Can you see my slides?
Yes, we can. You can put it in presenter mode, so you're good.
Okay, thank you. Again, welcome everyone to the Pacific Northwest Hydrogen Workshop. So Shannon has made a great introduction of this. So in this workshop, we invited industry leaders in this field, and to share their vision, discuss challenges, and how academia and national labs can help. So here we list those companies. So we really want to thank them for sending their expert to this event. So that ranging from hydrogen technology solution providers to the hydrogen technology end users, Microsoft, Cummins, Envision Energy Group, Ballard Power, New Hydrogen, and Plug Power. So JC Dream and Pacific Northwest are helping organizing this event. So this is today's agenda. So we'll have two sessions. Session 1, hydrogen production, will be moderated by my colleague Olga Marina. So the panel speakers include Cassie Iris, Qingying Jia, and Hui Xu. So session 2, that will be on hydrogen applications. So will be moderated by Aaron Favor. Our panelist speakers include Ronan Arunach, Max Timenti, Mark Monroe. I hope I get the name correctly. So for each session, we'll have a QA after our speakers. So let me introduce our two moderators. Aaron Fever, he's the director of JC Dream, Joint Center for Development, Deployment and Research in Earth Abundant Materials. So it's formed by Washington State Legislature. So Aaron is a global expert of moving technology from lab to industry to deployment. Before he became a director of JC Dream, he co-founded the company called Energen 2. So he led the company from lab to a venture-backed business. So Olga Morena is a chief scientist at Pacific Northwest National Lab. She's an expert on solid oxide fuel cell and solid oxide electrolyzers. So her work has been recognized by including Department of Energy Hydrogen Fuel Cell Office. She's also an associate editor for ECS Journal of the Electrochemical Society. So without further ado, I will hand it to Olga. So please take it from here.
Yes, hello everybody. It's great to be here. It is my pleasure to introduce to you Cassie Iris, who is a very distinguished scientist, and she is Vice President of Research and Development for NEL Hydrogen US. She joined NEL in 2007 and is currently responsible for developing and executing NEL's PEM electrolyzer technology strategy. She's involved in any aspect of the stack development, starting from the advanced cell development, materials development, designs and manufacturing processes, up to the product implementation. Cassie, the floor is yours.
Thanks, Olga. Let's see if I can get my slides up here. Sorry. You see the slides all right?
Yes.
All right, so I'll just quickly give a little bit of background on NEL so the other panelists can do the same for their companies and get into the Q&A. But for anybody who doesn't know who we are, NEL is about 500 employees. We're a pure hydrogen company focusing on water electrolysis and hydrogen refueling. So we have two production facilities on the electrolyzer side, one in Wallingford, Connecticut, which is where I'm based. That's where we make the PEM systems. We currently have been producing up to about 50 megawatts a year, but this facility can do about 150. And we are currently looking for a new site to expand. In Norway, we produce the alkaline electrolyzers. So we have a fully automated plant that was just commissioned this year, which is currently capable of 0.5 gigawatt of alkaline electrolysis, and they've already started procuring equipment for the second line. The building has space for up to 2 gigawatts. And then on the refueling side, we have a factory in Denmark, which can do up to 300 stations a year. So a little bit more on the Haroya plant. As I mentioned, this produces our alkaline electrolyzers. These systems were really developed for industrial applications from the beginning. So a lot of the cost has been taken out, but there's still room based on how old this technology is to incorporate modern automation, new materials, et cetera. But the NEL legacy goes back 100 years. And we've already demonstrated this technology at 100+ megawatts. There's a picture down below of one of our factories that operated for about 40 years. And as I mentioned, this new facility can produce up to 2 gigawatts. Just some of the examples of projects on the alkaline side that are either already installed or have been announced. And just to give a sense of the types of scale of systems that are going up today and what types of applications. So we have electrolyzers feeding a chemical process, which is about 9 megawatts of capacity. There's areas looking at home heating. That particular project is 5 megawatts to serve a community. Green steel is similarly about 5 megawatts for this particular demonstration, growable to much larger. And then mobility and mining are two of the other applications that we already have systems going into. So there's a wide variety of areas where renewable hydrogen can impact, and there's lots and lots of projects going on around the world for both PEM and alkaline. Our Wallingford facility has about 125 employees, and we're growing rapidly. We hired somewhere in the neighborhood of 15 to 20 positions last year, and we have another similar amount open right now with continued growth expected. We've delivered over 3,000 systems to date. And you can see just the growth in terms of the types of units that we're producing and the total installed capacity base over time. So you know, we have systems in the 100+ kilowatt range going all the way back more than a decade. And our megawatt platform has been around for about 8 years now. So we're growing quite a large base of products in these areas with about 70 megawatts installed to date, and several more projects that have been announced. In terms of where the PEM products are mainly going, so it's really more suitable for things like offshore wind applications because of the footprint needs, as well as the fact that you're tying directly into a wind turbine and the response times needed. We also have several projects in bus and truck fueling around the world. This particular one is in California. And we also have a green ammonia project that we've been doing with Iberdrola, which is the largest PEM installation that we have at 20 megawatts. And that was just commissioned, or is in the process of being fully commissioned, has been partially commissioned this year. So one of the topics that we were asked to touch on was benefits of lab and industry collaboration. So this is a slide that I've presented in other forums because I think it's a really great example of how we can move from a conceptual design and fundamental understanding all the way to commercial production. So this was our bipolar plate project that we implemented several years ago. I still have my ECS transactions paper from 2010 referenced a lot of places, and I have to keep saying it's not accurate anymore, because in that paper, at the time, the bipolar plate was the most expensive component in the stack, but this project changed that. So this was a project where we were able to go from kind of clean sheet of paper, look at analysis of different plate designs, look at the stresses, look at the flow characteristics. We worked with Oak Ridge to look at different coatings and how that impacted hydrogen embrittlement in the part. And we looked at completely different ways of manufacturing the plate. And through this effort, we were able to reduce the cost of that component by effectively 80% in terms of both the manufacturing changes and the scale up that we did. So this component really forms the basis of our two largest cell stack platforms. We developed it initially at about 100 square centimeters and then scaled it to 700 and almost 1600. And we've fielded thousands and thousands of cells with these configurations. And then finally, looking more forward, roll-to-roll development is another area where we've been leveraging a lot of the lab capabilities. This is now the most expensive component in the stack, the membrane electrode assembly. And so understanding how we move that from a fairly low volume manufacturing process with thick membranes and high catalyst loadings to a much more streamlined part. We've been working on this for a few years now through a DOE project that we've now moved towards an internally funded project to commercialize it, and that's actively underway. But really, we started from understanding all the different materials, the ink formulations, the coating parameters, to scaling it up with a pilot line. This is an example of the roll-to-roll coater at NREL. We've also worked with Oak Ridge, and then scaling that to a more of a production scale on toll manufacturing equipment before we go ahead and purchase our own. So we had a collaboration here with NREL and Oak Ridge, and there were other national labs involved in the roll-to-roll CRADA, which I know Plug has been involved in as well. And NREL also is helping us with figuring out how, if we can make the parts, that's one thing, but we also have to inspect them at the same speed because you don't want to be making a bunch of scrap. And so that's an area where they have expertise as well. And so you can see moving from the baseline, there's so much we can do in optimizing the process we currently have, but really moving to roll and more advanced materials is what really brings us down to those similar cost reductions as we saw with the bipolar plate. So finally, just some thoughts. I think electrolysis is going to go through a lot of transitions in the next few years, a lot of scaling up in manufacturing of components and stacks. There's a lot of opportunities for material and process optimization throughout the supply chain, moving to robotics, automation, lowering the amount of noble metals we're using, et cetera. And all of that requires high strength and fundamentals because we need to maintain reliability and quality over all kinds of applications, duty cycles, et cetera. And I think that the partnerships certainly result in faster progress and deeper understanding there. So I'll turn it back to Ola.
Thank you very much, Cassie, for a wonderful overview of the technology and the challenges and the path forward. I'm very pleased to introduce our second panelist, Dr. Qingjin Yan, who is the principal project scientist at Plug Power. He joined Plug Power in 2020 after holding a research associate professor position at Northwestern University. He obtained his PhD in material science from Illinois Institute of Technology in Chicago, and he is an expert in the catalyst development and characterization, mostly focusing on the fundamental understanding of the kinetics and mechanisms of the electrochemical reactions. Dr. Jia, please.
Thanks for the introduction. This is Jia from Plug Power. Today, I would like to briefly introduce Plug Power and our vision of the green hydrogen business. Plug Power is the industry leader of the end-to-end green hydrogen ecosystem that includes the hydrogen production, transport, storage handling, and then application as end user. We have with a variety of applications. We have customers including Amazon and FedEx and Walmart. But today I would like to focus on the green hydrogen production part. So basically at Plug, the green hydrogen is produced via water electrolysis, via PEM electrolyzer. And our efforts are to build and develop and build large-scale electrolyzer globally and to provide affordable green hydrogen. And this year at Rochester, we already have this plant with a capacity of 2 gigawatts at this year. And the next year, we're going to have another plant with the same capacity at Perth, Australia. And in the next couple of years, we're going to have a plant in South Korea and Europe. And on the photo here is basically, one typical alugas stack was built in Plug here. And we have different scales of electrolyzer. On the left side is the 1 megawatt, and in the middle side is the 5 megawatts, and on the right side is 10 megawatts. So basically, for a typical expansion is for example, the 1 megawatt system, you can generate around 425 kilogram hydrogen per day. And in addition to these, photos, here is the real deal. So basically, this is a 10 megawatt plant that has been built. It's been built in Georgia, United States. So this is basically a typical image of that. And the plan is to generate 500 tons of hydrogen per day, in North America by 2015, and 1,000 tons per day globally 2028. That is basically the plan. And one of the major R&D efforts here at the Plug is to reduce the cost of the electrolyzer and or the green hydrogen to make sure the green hydrogen is competitive to other energy sources. So on the left side is a typical cost analysis of a typical MEA. So for the past 2 years, we have been able to reduce the cost of MEA by more than 50% from here down to here. And in the future, by optimizing the MEA, and basically there are 2 directions to reduce the cost. If we maintain the current density and increase the efficiency from 75% up to 85%, we can reduce the cost of the energy by around like 15%. On the other hand, if we maintain the same efficiency but increase the current density from 3 amp to 6 amp, we can basically reduce the cost of the stack by around like 50%. That is a big saving, and that a major reason behind that is basically we can use less stack to make the same amount of hydrogen per day. So those are basically 2 major directions to save the cost. And there's another concern of Electrolyzer or the green hydrogen generated by the Electrolyzer is the use of the iridium. So the iridium is not only expensive because it is the least noble metal around the world, as shown on the left side. And right now, approximately, basically, we generate like 8 tons of iridium per year, as shown here. This is right. And because of the very limited source of iridium, the iridium price basically increased very sharply recently because of the increasing demand of iridium. So it becomes a very expensive part of our MEA. But that is not the only concern. But that is not the major concern. The major concern is we don't have enough iridium to support all the electrolyzer, because the electrolyzer has been expanding very fast. So you can see that the sharp increase of the iridium price here is probably due to the demand increase by the electrolyzer, and also there are other demand for the electrolyzer. So I think there's a mismatch between the iridium we have and the iridium basically in demand. So one solution for that is to decrease the iridium loading in the PEM electrolyzer. And fundamentally, it is feasible because, according to the fundamental of the chemistry, at higher current density, basically we need less iridium. For example, here, if at a 0.5 amp per centimeter square, basically you can see that the performance is reduced with lower iridium loading. But if you go to like 5 amp per centimeter square, the performance is around the same, even with the very different iridium loading. So that is basically the fundamental, the feasibility of lowering the iridium loading. And practically, basically, there are several kinds of different advanced iridium-based catalysts that can decrease the iridium loading by 1 order of magnitude. For example, the top one is one typical supported iridium catalyst developed by Giner and right now at Plug Power. And the bottom one is another supported iridium catalyst developed by 3M. Even though those 2 are 2 very different catalyst systems, they can basically reduce the loading by 10 times with similar performance. So which means that practically it is possible to reduce the iridium loading without sacrificing the performance, which can potentially resolve the limited source of iridium issue. And this is basically estimation of how much iridium we need in the future and the cost. So, but around 2032, if we can increase current density to the 6 and reduce the iridium loading down to 0.1 milligram per centimeter square, so basically we can reduce the cost down to nearly $2,000. And let's say if by 2032 we can reduce the loading to basically to make the iridium the cost is around like $10,000 per megawatt. And if we increase the lifetime down to 20 years, you can see that we can only need the cost for the iridium is like 10 cents per kilogram of hydrogen. It's not too bad, assuming the 8% cost of capital. But of course, you can see from here that it is very important to increase the lifetime, not only that can reduce the cost of the uranium, but also can, how to say that, reduce the cost, make the recycling less important. Basically, you can see that the shorter lifetime recycling becomes more important. If the lifetime is 5 years, the recycling can significantly reduce the cost of the uranium. But if it is long enough, you can see that it plays a minor role. So this is basically the vision regarding whether we can reduce the uranium loading and whether it is feasible. But the key question is, I think here we need a lot of R&D help from national labs and universities, is how we can reduce uranium loading down to 0.1, and in the meanwhile increase the lifetime, which by far is the most difficult and the tricky challenge there. And I believe by far nobody knows the answer it. And that I think is where the R&D and also our R&D team at Plug is working on. I think this is a big direction, a big challenge to go. And that'll be all. Thank you.
Thank you very much. And you almost answered all my questions that I was going to ask you.
All right.
Our third panelist is Dr. Yuyan Shao, who is the CTO, Green Hydrogen, and at Envision Energy Group. He joined Envision Energy earlier this year, and he was a CTO at Giner, where he managed and oversaw component and design and system development for a variety of energy technologies, including low and high temperature fuel cells, water electrolyzers, and also working on CO2 conversion. Dr. Yuyan earned his PhD in chemical engineering from the University of Connecticut. And Yuyan, the floor is yours.
Olga, thank you for your very nice introduction. I would like to start sharing my screen. Can you see my screen now?
Yes, we can.
Okay, great. Hello, everybody. My name is Yuyan Shao. Currently, I'm the CTO of Green Hydrogen for Envision Energy. Before this, I had been working for Giner for about 12 years. So just give you some more introduction of Green Hydrogen for Envision's Net Zero vision. So Envision is a global company aspired to solve the challenges for a sustainable future, to create a world of beautiful energy. At this point, globally, we have 6,000 employees. As Envision, just give you an introduction of Envision's business units. The first is Envision Energy, that includes wind turbine. Actually, if you look at the website, Envision actually is one of the largest wind turbine and producer in the world. This part also includes that Envision and energy storage and power to chemicals. The second part is about Envision's digitals, basically how to use smart software to control the solar or power efficiency to get that to achieve the best trade-off between that power and lifetime. And third is Envision ISAC. Actually, this part really work on that large battery for the electric vehicles. We have been working with some larger car manufacturer like Mercedes-Benz, BMW, Honda. This I can give you the global price of Envision. Basically, you can see that it covers 3 regions. One is about Europe. This including the France, digital center, and electric vehicle EV center, and also the UK, London, and Denmark, Germany. And the Germany, actually, there are 2 units. One is engineering center, the other is Gearbox Innovation Center. The second region is really in the Asia, that include China, the Japan, and Singapore. The third region is North American. At this point, we have locations in Silicon Valley, California, Colorado. Actually, this is the one of the premium global design center in the world. Also, the Digital Energy Center in Houston. Innovation has a very large battery manufacturing center in Tennessee. And then we are at this point, we are going to build another battery, a gigawatt battery center in Kentucky in the next few years. Right now, you can see that we don't have any location in the East Coast. So I'm leading an effort of building a hydrogen center in the Boston area. So just give you some recent news, share some recent news about the innovation. 3 months ago, Innovation ISAC announced a $2 billion EV battery gigawatt plant in Kentucky, and this will, when it's in the full operation, it will produce 30 to 40 gigawatt hours of battery. This is expected to be sufficient to up to 300,000 vehicles. Actually, this picture actually shows that innovations, existing innovation buildings in Tennessee. Just about 2 days ago, Innovation signed a strategic partnership with the government of Spain to build the first light zero industry park in Europe, which include 4 projects. The total value is about 3.8 billion euros. This includes battery production, renewable energy generation, storage, and green hydrogen. So let's talk about green hydrogen. So Innovation's green hydrogen strategies. Innovation aim to build the multiple light zero industry park, like the one we are just talking about in the Spain, in Europe, United States, South Asia, and China. So this industry park, like we call the DZIPs, we are systematically integrate the renewable energy generation with the green hydrogen and later downstream industry application. For instance, Innovation is one of the largest wind turbine producer. It will integrate the wind turbine and then green hydrogen production and then hydrogen end user. That means that when Innovation tackle these challenges, we are not only look at one step, only like hydrogen production. Basically, we look at this all those steps together. So like green energy generation, green energy conversion, and then the green energy hydrogen utilization. For instance, like ammonia synthesis and petrochemical upgrading. So you might heard that a lot of we are asking the questions. Oh, the green hydrogen is so hot, and what will be the hydrogen's end user, right? That's actually the Innovation is pretty much is very focused on this, really the utilization of green hydrogen. In order to meet this needs, Global Hydrogen Center of Excellence, we call it Hydrogen COE, has been launched in the Boston area. This center will pursue advanced water electrolysis technologies, engineering designs, and manufacture readiness. So this center will function as a technology hub serving Innovation's global hydrogen needs. At this point, that we are very aggressively bring in talents in very diversified areas. We are going to fill about 40 vacancies in the next 1 year. So if you would be interested in the opportunity at Innovation, please let me know. This is only the center. In the meanwhile, Innovation really look at gigawatt factory. Innovation's gigawatt factory across nations, different countries under deployment, because Innovation really has tremendous capability in engineering design, supply chain development, and mass manufacturing. So If you look at the innovations, electrolyte technologies, really we have been focused on the low temperature water electrolysis technologies, but with different focus. One is this is alkaline and liquid electrolyzer. This technology has been existing for many decades, but it has gained and moment recently has gained the moment because it's a low price. And for this technology, we are working hard to improve current density. As we know that currently for the commercial product, current density is only about 500 milliamp per centimeter square. So we hope to improve current density by 3 or 4 times. For the PEM electrolyzer, the focus is the cost reduction. A moment ago, Jia talked about the iridium price, or Ali, Cassie talked about other expensive components. So innovation trying to use our expertise resources to reduce the cost tremendously. The last one is AEM, electrolyzer technologies. This is more advanced technologies. Right now, the concern is the lifetime. So we are working with the summer membrane companies trying to improve the lifetime of this AEM electrolyzer. So I think that's a very brief introduction of the company. So please, this is my email contact. If you have any questions or would be interested in the opportunity and innovation, please let me know. Thank you for your attention.
Thank you, Hui, very much for your interesting presentation. So all of 3 of you were talking about different electrolyzers for hydrogen production. And but there are other technologies to produce hydrogen. What is the most appropriate way to make green hydrogen? Would it be alkaline, PEM, SOEC electrolyzer? Or should we also consider maybe methane pyrolysis and fossil fuel conversion with carbon capture?
I would say the simple answer is whatever's cheapest for that set of conditions. So I think there's room for a lot of technologies. You know, high temperature is good when you have a heat source that's maybe not quite as mature as alkaline and PEM yet, but I think that's where its sweet spot is going to be. Alkaline is good for large areas where you have plenty of space and relatively slow ramp rates, and PEM is good for more of the constrained environments and high dynamic range.
Thank you, Cassie.
Yeah, I would like to follow up with Cassie. If you ask the technology readiness for green hydrogen, I would pretty much see that my preference is water electrolysis. It's not because I have been working on the water electrolysis for decades. It's because other technologies like PEC technologies, thermochemical technologies, even methane reforming with CO2 capture, that all those technologies are not ready yet. For green hydrogen, that if you really want to utilize technology immediately, the water electrolysis is the most viable approach. And then let's talk about that water electrolysis technologies in terms of low temperature, high temperature. Yeah, as Cassie pointed out that if electricity is very high, right, you really focus on efficiency, and then high temperature electrolysis will find its application, because otherwise the cost will be too high, right? And then if you can get a very cheap electricity and a low temperature electrolyzer like alkaline and PEM, yeah, they should be the first candidates.
Great, thank you, Hui. Another question I have. At the European Solid Oxide Conference in Lucerne just a few weeks ago, there was a presentation on green hydrogen demand. And the calculations showed that we need to increase the electrolyzer manufacturing capability by 30 to 100 times. When do you think we can meet that demand? And also, what steps should we take to get there?
I mean, I can start again. So I think most electrolyzer manufacturers who have been around a while are already announcing gigafactories and things like that. So I think certainly by 2025, if not before, we would be expanding the total global capacity of electrolysis by those kind of numbers. Things that have to happen. I mean, the infrastructure bill for the US is certainly a good start. There's other initiatives in Europe, but it's really funding that component development, investing in manufacturing, getting the factories up and built. Those are the things that need to happen.
And so then I'll ask the following up question. And you actually briefly touched it in your presentation. What are the top manufacturing challenges for each electrolysis technology? Can you also maybe talk about the alkaline PEM and salt oxide?
So for alkaline, I would say it's trying to get to higher current density. So traditionally, those have been very low current density. So coming up with new electrode structures that can still be made in these relatively simple ways, but can double or triple the current density. I won't comment on solid oxide because you're definitely a bigger expert in that area than me, but
You know it all too.
but PEM, I would say it's the things we've all talked about. You know, it's investing in the manufacturing and taking all the learnings from other PEM devices. But I'm sure Plug and Envision have thoughts on that too.
Please.
Yeah, for the PEM right now, the supply chain is one big issue. Long term, I think the major concern is to reduce the cost, and to apply, for example, DOE has this target, $1 per kilogram of hydrogen. That is a big challenge. So how to reduce the cost of the stack and to reduce the cost of the green hydrogen to make it affordable and to customers and make it competitive to other energy sources. That is a very big challenge. And because I'm a catalyst guy at Plug, from my perspective is the battle, between the demand of the iridium and also the supply of the iridium. There's a big gap, in the next, let's say, a couple of years, in the next decade, and how to reduce the iridium loading without sacrificing performance. I think that is a very big challenge here. And also, when reduce the iridium loading, how to keep the lifetime, because for electrolyzer, the lifetime is supposed to be more than 10 years. I think that, and also the lifetime also affect the cost of iridium significantly. So I think those are big challenges here, and also parts we need a lot of help from R&D. Yeah.
Okay, thank you.
I agree with what Jia and Cassie said, that for the PEM, really the supply chain has been challenges. It used to be a very small market. Right now, the demand has increased tremendously. So we have to travel across different countries to find the best vendors for the PTLs, for the other kind of components. Sometimes they have spent a lot more time on the supply chain and then the technology itself. So you asked the first question about manufacturing scale up. You might have already seen from my slide that, from innovation point of view, that really have very aggressive plan in the next 5 years to have 2 gigawatt plants. One is in the US, the other could be some other countries. So that's basically, yeah, our target. So yeah.
Okay, great, thank you. So since we talk green hydrogen, what would be the greatest challenge for the integration of electrolyzer technology with renewable energy, like solar and wind?
Yeah, I can start with this one first. So since I have been working on this area for a while, so when we look at this, really look at I think the first concern is about that intermittency, like how the intermittency of renewable energy will affect electrolyzer operations. So there are a lot for wind and for the solar, the renewable profile is different, right? How this would be whether it be long-term effect or detrimental and to the lifetime, how would the catalyst would degree with this intermittency. So the other consideration that if you like build that electrolyzer near the sea, you have to use that sea water, right? Like and then how the water treatment could be an issue. And if you have like water treatment, water like contamination intrusion, how will this contaminants affect the lifetime performance of electrolyzer? That's one consideration. The other really about integration from, for instance, the power electronics supply, power electronics actually is become very important component of electrical system. So how to design that power electronics exclusively for the electrolyzer, that is also challenging. Give one example that like Envision is the wind turbine producer. We are like trying to put that electrolyzer next to the wind turbine, or even in the chamber of electrolyzer. In this case, like what design would be changed to fit that electrolyzer into the wind turbine, the chamber, right? That's another another challenge. Yeah.
Yeah, I agree with what Hui said. I would like to add a few points. I think, by using the renewable electricity, it's a mutual benefit. So one thing we haven't covered yet is the cost of electricity. The country is still very high, right? If we can significantly reduce the cost of electricity, that would be great. Can significantly reduce the cost of the green hydrogen. And by using the renewable energy from solar or the wind, we can reduce the cost of the electricity. And on the other side, for the electricity generated by wind or solar, it is very hard to integrate them into the grid. So, and in this case, by using the electrolyzer, or basically you can imagine the hydrogen as an energy carrier to basically store the electricity generated by those solar and wind, and then we can basically use those electricity. We can see that it's basically combine two things and can do mutual benefits. I think that is a great thing to realize.
I would just add on the more practical side, we've dealt with many customers in a lot of different areas. And one of the challenges that you tend to run into is whenever you're doing something with a new customer for the first time, there's a lot of debate over who owns what piece. So when you're talking about the integration, it's who owns the interconnects, who's going to do certain processes on site, all of those types of things. And it's working through all that I think is what takes some of these projects so long. And as we have more and more of those out there and we're working with the same people over and over again, that will streamline significantly.
Great, thank you so much. Since we're talking about integration, I cannot but ask about the energy conversion and storage as well. So how do you view electrolyzers as a means of energy conversion and storage compared to, for example, battery or other storage technologies?
I think first of all, storage is storage, and we have to remember that. So, some people complain that hydrogen is not going to serve everything, and that's completely true. I mean, if you have solar or wind that you can use right away to power something, that's as a primary source, that's what you should do. It should be the excess that we're storing. And in that case, I would say batteries are very good for very short term, few hours types of needs. But if you're talking about overnight, weeks, seasonal, that's where you need something like hydrogen.
Thank you, Cassie. So
yeah, I would like to add to Cassie's point that yeah, definitely long duration storage is the advantage for hydrogen. We calculate that if you do the storage only like a few hours, of course, battery it clearly has advantages. But if you do like storage like 2 or 3 days, and then no doubt that hydrogen will be the winner. The other sort of really about the flexibility. If you store the renewable energy only in the battery, that's an electron. They can only for electricity, right? But if you store this renewable energy chemically, like in hydrogen, first it would gain tremendous flexibility. You can still go back to electricity, And if you can go, you can still hydrogen can be combust, and also it can be used for the other industry processes, right? The more flexibility and long duration storage are two clear advantages.
It's a great point, and it leads me to my next question. So it appears that PEM and alkaline electrolyzers more easily produce hydrogen at elevated pressure, although it's far away from 700 bars that one would like for compressed hydrogen for cylinders. And the cost of compression is significant, we all know it. So if we need to produce hydrogen at a larger fixed facilities and then transport it to somewhere else where it's maybe needed, the transportation become critical and delivery. So can you talk about maybe how do we store and convert hydrogen to liquid fuels, maybe ammonia or something else?
I think, again, it's going to depend on the application. I mean, if you want to ship things, hydrogen, for example, over the ocean, like the Australia-Japan collaborations that have been going on, something like ammonia could be, could make the most sense. In fact, I think Plug's CEO just said that to the Senate a day or two ago. But I think for other types of distances and applications, it's not, it does take quite a bit of energy to go to ammonia and back again if what you want is hydrogen. So I think it's going to be kind of case specific.
Okay, great. Thank you so much. Being a national lab employee for many years, I cannot help but ask you about how national labs and academia assist and can further assist all of your manufacturers in scaling up your manufacturing capacity, and what could we do to accelerate your programs?
Yeah, Olga, I can talk about this first. Please. So you were asking at how academia, national lab can help industry, right? That's basically your question. Yeah, I think we can look at it in two ways. First, that really need that academia to train more highly qualified candidates, scientists, engineering for electrolyzer industry. I said so because electrolyzer used to be a very small job market. Suddenly, in past few years, this market has been booming. So really the highly demand. You can ask Cassie, ask Plug Power. So everybody has been looking for really strong candidates. So first that we are looking for people who really are good at electrochemistry, right? That's knowing how this electron work, improve the performance. And then we also want to look for that mechanical engineer who know how to build a stack, look at stack engineering. But you combine this, more importantly, we are looking for electromechanical engineers who know both electrochemistry and mechanical engineering. This is extremely important for us. The second sort is about that some fundamental studies. Like industry, we are really target driven, that we want to improve performance and we want to scale up, but really don't have adequate resources and time to look at the fundamental studies. For instance, the catalyst decay, the interface, electrode membrane interface problem, the electrolyte degradation. Those are things are very important. But industry cannot look at this, but the academia can really play an important role regarding this.
Yeah, when we said, I have added a few more. I think the national lab have some resources that industry will not have. For example, make more specific examples like characterization. For example, national lab can have synchrotron based X-ray and nano CT and the very high, how to say that, high-end TEM and to look at things at the atomic scale, and to look at things under in situ and operando conditions. All those capabilities, there, we can basically national labs have resources in terms of equipment and people to do that. And industry apparently, we don't. No industry can afford like a synchrotron center, for example. And in that regard, I think industry need a lot of help and collaboration with national labs.
I would just add, I think that the national labs can really help us accelerate. I mean, I think a lot of the things are things we could do ourselves if we had the time, like the number of years, but we don't. We have to move quickly, especially if we're going to be competitive worldwide. And things like the Energy Materials Network consortiums, where we could leverage national labs for specific tasks and areas of our projects. The consortia that are available now, H2New, the CRADAs, I mean, I mentioned the roll-to-roll one. I think those gather significant brain trusts in these areas that we can leverage to just help every project move more quickly, which is what we need right now.
So to summarize, brain support and workforce preparation and talent training, right? So it's a huge responsibility for academia to step in now and to ensure we have trained people to join the companies, growing companies. Well, thank you very much, you all, Cassie, Ching, and Hui, for participating in this panel. And I really appreciate your time and great presentations. And I'm giving word now to Aaron. Thank you very much.
Thank you.
Thank you.
Aaron, you're on mute.
Yeah, thanks everyone. I wasn't sure if I was waiting for an introduction or not, but thanks everyone for your time today. Sorry I couldn't join the earlier conversation. I've been in the middle of helping here at the Port of Seattle to pull together the hydrogen hub effort that we're focusing on here in the Pacific Northwest. So I'll just go ahead and introduce myself briefly, and then we can. I'd like to share a little bit of information about what we're doing here. I don't want to take too much time away from the panelists, but so my name's Aaron Fever. I'm the director of JC Dream, which is the Joint Center for Deployment and Research in Earth Abundant Materials. We are a Washington State run organization based out of Washington State University. And we focus on critical materials challenges in the clean energy and transportation sector. So that can be things like battery material challenges with cobalt or lithium in lithium ion batteries, or rare earth elements in electric motors, wind turbines, and the like. But in the hydrogen economy, it's a lot of the catalysts that we find ourselves using in electrolyzers, fuel cells, and even alternative fuel production. So we've put an emphasis on that hydrogen space here in the state of Washington, recognizing that Washington State has a huge opportunity in the hydrogen space with all of the clean energy and hydropower that we have here, as well as our transportation industry being largely focused on heavy duty transportation. We recognize that this is a huge economic and technology opportunity here in the Pacific Northwest. So we've been working on creating a hydrogen hub opportunity here in the region. I'm now the director of the CHARGE Innovation Cluster Accelerator Organization. CHARGE is the Consortium for Hydrogen and Renewably Generated E-Fuels. And we're a cluster organization that focuses on aligning researchers, industry, government, and all the players that are going to be needed to engage in this kind of a hydrogen hub opportunity. So I might share a couple of slides real briefly to show you guys what we're thinking about here with the Pacific Northwest Hydrogen Hub. Let's see. I'm going to share my screen. Hopefully that works. Okay, I think that's working. So the concept here
Aaron, you
is,
may want, oh, perfect.
is that working?
Yeah, perfect.
Cool. So the Northwest Hydrogen Hub, we're going to divide up into subregions where we want to geographically align the production, make, move, store, and use is what we call it to simplify things. Production, transport, storage, and consumption of hydrogen all in geographically compact regions, and then provide hydrogen within those subregions. So this is a handful of the different types of things that are already going on around the Puget Sound region. So we've got companies like First Mode that have developed hydrogen earth movers. We've got Puget Sound or All American Marine has developed some of the first hydrogen ferries. There's a big emphasis on ports. Here, I'll show you all. I don't know if that shows up or not. I'm actually at the Port of Seattle right now talking about how we utilize hydrogen to reduce emissions in port operations, oil refineries in the Puget Sound region. All of these are areas where we're putting some emphasis. And this just kind of shows you some of those make, move, store, and use projects that are going on in the region around the Puget Sound area. In Eastern Washington and Northeast Oregon, we have a similar story. There are a number of hydro dams. There are data centers, there are warehouses and opportunities for utilizing the Columbia River, both for production and transport, and then aviation. Hydrogen-powered aviation is another area that we're focusing on. And you can see the same sort of thing. This is maybe not make as most sense to folks outside the region, but this is the upper Columbia River where a lot of the hydro assets are in parts of Eastern Washington and Eastern Oregon. So anyway, I don't want to take too much time, but that's just a quick overview of some of the things that we're considering as part of our hydrogen hub here in the Pacific Northwest. And I will go ahead and introduce our first panelist, who is Ronan Arunach Cummins. And Ronan is the director for the program for the new power business unit. In Ronan's previous role, he was responsible for the power electronics and motor generators product line at Cummins, launching the product line earlier in 2018 and leading development programs for a number of products integrated into hybrid, battery electric vehicles and fuel cell powertrains. Before joining the new power business unit, Ronan held a number of commercial positions at Cummins, aftermarket in Europe and North America. Prior to joining Cummins, Ronan worked in the semiconductor industry. And I will also just highlight that Cummins is an important player in the Pacific Northwest and one of the electrolyzer producers for some of the first projects that we've seen here in our region. So looking forward to hearing what you have to say, Ronan.
Excellent. Thanks, everyone, for the introduction. So, yeah, I prepared a few slides just to introduce Cummins, a few of the projects we're doing. So I'll share my screen. Just let me know when you can see it.
Looks good.
Yeah, perfect. So a short introduction on Cummins, how Cummins is structured and built. Cummins has 5 business units in total, 100 years old. Was planning on using my 100 years t-shirt, but I didn't know if a t-shirt was the okay shirt for this occasion, so I switched. The biggest business unit that we have is obviously the engine and the diesel engines. We have a power system making generators, making components for all of these power systems and engines. We have a very large distribution network, and our newest business unit, which is where I work, and I've been working the last 4.5 years, is what we call new power business unit. From a Cummins perspective, I think the main goal, and Cummins has an initiative called Destination Zero, which aims at getting to zero net emission by 2050. And the goal is to reduce emission and be a power of choice for all of the different technologies that exist, right? Or maybe not all of them, but at least what our customers would like. So a customer would be able to take a different technology all by Cummins. So obviously we have the traditional diesel powertrain, which there is a lot of investment on reducing emissions on these engines as well. today. There's the natural gas powertrain. We have hybrid electric, so batteries and engine together, the fully battery electric, and the fuel cell electric. From a fuel cell and core technologies of our new power business unit, and we are structured into 4 different businesses, or 4 different product lines, I would say. The fuel cells is where I am working at. And we have hydrogen generation, stationary fuel cells, and batteries. A little bit about our new power business unit. We are about 1,400 people out of the total over 60,000 Cummins has. So compared to the rest of Cummins, we're relatively small, but still not very small and growing quite fast. Cummins is located in over 190 countries, and I will show a little bit about where our new power facilities are located. But there is Cummins representation on almost every country that the US is allowed to do business with. And we have over 70 years of combined hydrogen experience through some of the acquisitions that we have made. Over 500 battery electric powertrains in the field, 600 electrolyzers, and over 2,000 fuel cells powering in demo vehicles and commercial operations. A little bit about the Cummins journey and how we got involved with new technologies and why are we positioned well there. Cummins was actually investing in new technologies and zero emission technologies for quite a long time internally. But in 2017, really the big push came out and Cummins started with a number of different acquisitions. So we acquired 2 battery companies in 2017, Bramo and Johnson Matthey. Later on, we acquired a number of other companies, mainly in the drivetrain solutions, such as EDI in California. The biggest acquisition for the related to hydrogens was mostly the Hydrogenic acquisition that took place in September of 2019. And that's where our main strengths, I would say, in the fuel cells area coming from. We then joined a joint venture with Enprox for hydrogen tanks. So essentially looking at this whole supply chain of hydrogen. And in November 2020, the name of the business was actually changed from Electrified Power to New Power, just to include all of these new hydrogen technologies. And that's how Cummins acquired a lot of the capabilities we have today on all of the new technologies. From a footprint perspective, that's a map that describes where we are today. And we're working really close to the customers and that we have. The main facility that we have is in Mississauga, Canada, next to Toronto. And we have a fuel cell operation there and an electrolyzer operation. We have a pretty big facility in West Sacramento in California, supporting a lot of our North American customers. A pretty big facility in Germany as well, supporting a lot of the project and customers we have in Germany. And same for electrolyzer business, that we have a lot of facilities in Germany, soon to have a facility in China, and soon to have a facility in Spain as well. So from a Cummins perspective, we're looking at this whole value chain and ecosystem of hydrogen, right from the production of electricity, which Cummins is actually a big participant through our power generation business unit, all the way to hydrogen storage and electrolyzers, and obviously going to the end user and the fuel cell electric vehicles and any other applications that we may participate in. From a product perspective and what we do, we start from the single cell, and that's specifically probably my product line, the fuel cell, the PEM fuel cell. And we also go through to the power module and eventually to the whole fuel cell system, being modular and being adaptable to the customer needs. And I have a few examples of vehicles and projects that we have done and have in the field. And some of the existing projects are on Scania trucks and Alstom passenger trains. And these are actually operating today in Europe. And we also have quite a few demonstrators, as can be seen here in the images. The Class 8 is actually a vehicle that was prepared for the Port of LA using our fuel cells and some of our power electronics as well. And we can see the range of applications that Cummins has participated in. Just a bit of the highlights of the recent projects that were announced. So this is the truck that is started operation in the Port of LA. It's actually a Packard truck using our HD90 fuel cell and Cummins Power Electronics. These are two new announcements of cooperations and projects we are doing, one with Daimler Truck in North America and one with Scania in Europe. And essentially the idea is to start having these trucks on the road in 24 and beyond. And some of the projects that we have on the electrolyzers, essentially we have both alkaline and PEM. So these are some of the locations that we have alkaline projects in Colombia, India, Russia, and Brazil, and some of the locations that we have the PEM project. And I don't see the one in your area on here, but we should add it. So that was briefly about Cummins, and that's what I had.
Thanks, Ronan. Very, very informative. Yeah, the electrolyzer here in Washington State is set to be installed this fall or early next year.
So once it's installed, we'll take an image and add it to my presentation.
Yeah, it'll be at Douglas County Public Utility District at the Wells Dam in Eastern Washington. So we'll keep an eye on that one. But sorry, I missed the first half of the panel. So are we doing questions after all the panelists have spoken or in line?
Yes, Aaron. That's the other speaker to talk and then do a Q&A session.
Sounds good. So next we'll go with Max Cimenti with Ballard Power Systems. So, and I will introduce Max. Max is a principal engineer and scientist at Ballard Power Systems. He obtained a PhD in chemical engineering from the University of Calgary, working on anode materials for the direct utilization of alcohols in solid oxide fuel cells. In 2008, he started working on PEM fuel cells, where he was involved in electrocatalysis research, cathode and anode electrode engineering and design, and advanced methods for in situ characterizations of membrane electrode assemblies. He's currently leading a project on MEA components integration for the Ballard next generation products. Max, go ahead.
Thank you very much. Let me share the screen here. Oops. I hope it's showing right.
Looks good.
Okay. So I'd like to start actually by thanking the organizer for the opportunity to participate to this discussion and be part of the panel, and also to Ballard for supporting the initiative. So about Ballard, Ballard is a global fuel cell company. We have been active in research and later also on commercialization of PEM fuel cells, starting from 1979. The numbers that you see on these slides are meant mainly to give you an idea of our position in the business landscape. It shows what kind of applications we focus on, what has been demonstrated and achieved so far, and also the production capacity, some numbers on the production capacity that we have. So in this slide instead, we see a summary of the hydrogen powered products that we currently offer. These include stacks, fuel cell modules, and complete fuel cell systems designed for various applications. So the next slide is instead intended to answer the question, what vision do we have on low and zero carbon hydrogen technologies? So it's clear now that zero emission power is not just a radical idea. The global transition to clean energy is well underway, and the role of renewable hydrogen in difficult to decarbonize sectors and applications is also widely accepted. Zero emission economy of the future for the future will require both battery technology and hydrogen fuel cell. And while battery technology is preferred for short distances and small vehicle and short duration energy storage applications because of the inherently higher efficiency. On the other hand, hydrogen and fuel cell technology has an advantage for applications requiring high payloads, long or very long range, and rapid fueling needs. So Ballard can already provide a number of low and zero carbon technologies, solutions for heavy duty motive applications. And to be more specific, regarding bus and transit applications, in the previous slides were mentioned two types of stacks, like the FC Velocity HD and FC Move HD stacks, which are used to power several vehicles, for example, the New Flyer, Solaris, and Ride-Bus buses. Then in the truck sector, Ballard stacks are powering already over 2,300 urban delivery trucks in China. Regarding Class 7 and Class 8 trucks, we have projects, demonstration projects in California, and also we are active in mining trucks in China and in South Africa. For line haul freight trains, we are currently retrofitting a locomotive for a CP rail using a Ballard fuel cell system. This is just to give an example. And finally, in the marine applications, Ballard Europe is collaborating with various developers to decarbonize cruise ships, ferries, river barges using FC wave systems. So in summary, we believe that hydrogen fuel cell technology is the preferred solution to decarbonize heavy-duty transportation, and we already have solutions for this. So now the next slide is intended to sort of summarize what we believe the challenges are, challenges and needs to overcome to satisfy the near and future needs regarding fuel cell, PEM fuel cell technology, maybe focusing mostly on MEA technology. And this is one of the questions that I believe was intended for this panel. So the first aspect regards the MEA reliability for heavy duty applications. So now the main objective is to meet cost requirements for our products without sacrificing stability and durability. And to do so, we need a fine-tuned optimization of our electrode and MEA designs. And of course, trade-offs are necessary in this case. And we need to have a very up-to-date list of specifications and requirements for the components. This is extremely important for quality analysis and control, especially if we envision a high volume manufacturing scenario. We believe that a deeper understanding of the correlations between materials, electrode structures, and the properties of the components would help in this process, as well as improving our predictive capability of the key degradation processes. And of course, academia and national labs are key to address this kind of topics. So the second aspect is more related to the fundamental understanding of MEA processes and phenomena. In this case, we are specifically referring to improving and deepening our fundamental understanding of all the relevant phenomena, as well as our ability to model the physical and chemical processes occurring within the MEA. So just to give an example, we could benefit from simplified and faster models that allows us to predict the two-phase behavior of electrodes and where water goes in GDLs and within the electrodes, and as well as in the flow field, and how these properties and behaviors change with aging of the MEAs within the stacks, as these are used in real products in the field, as we say. Then the second aspect is about having reliable and predictive, again, models, and I mean here like physical models. So I'm referring specifically to conceptual understanding, but as well as maybe some mathematical models to be predictive in this case. Models of ORR and HR poisoning behavior, including reversible degradation, such as ionomer poisoning, the catalyst ionomer interface, as well as fundamental understanding of break-in and conditioning, as well as recovery processes in the MEA. And finally, it will become increasingly important to have reliable models to predict the combined effects of chemical and mechanical membrane durability, given the increased lifetime expectation for heavy-duty applications. We went from the 5,000 hours, maybe 8,000 hours in case of vehicles, to 35 and 50,000 hours now for heavy-duty applications within 5 years of, let's say, research. So the last aspect that we believe is still very challenging is to improve our ability to quickly introduce new materials and new maybe components into commercial products. So here I'm referring, for example, to novel catalysts, thinking about octahedral platinum nickel ORR catalyst, which could greatly improve activity, and they have been demonstrated ex situ in RD testing, or new ionomers, for example. It is very unlikely and probably impossible to apply rigorous design verification and validation for all combination of materials and subcomponent designs that come up. So we need to gain essential understanding of what the key properties of these new materials are, and how to integrate, and what the key tests should be for these new materials for a faster injection of these new materials and concepts in our products. So in conclusion, we believe that these three aspects of at least MEA technology, that's what this was intended to cover, can effectively be addressed in collaborations with academia and national labs. To conclude, I've put together a quick slide mentioning what type of collaborations we are focusing currently. So it's just 4 bullets. We focus on new materials with enhanced properties to allow cost reduction and longer lifetime. Again, I'm referring to catalysts, ionomers, and understanding how they behave, how they interact, and how we can best introduce them in products without having surprises in the field. Then the second is to let's say focusing on the fundamental understanding of the catalyst ionomer interactions and what kind of impacts this have on performance as well as on durability, and what kind of leverages we can play with. And then also material stability and impact on degradation by products. This should include also mitigating strategies, for example, what type of operating conditions or operating changes should be used to get rid of some poisons in real products. And finally, novel characterization techniques, for which, of course, national labs excel to define structural degradation through the lifetime of products. And this was pretty much it from my side. Thank you very much.
Fantastic. Thanks a lot, Max. I really appreciate that very interesting presentation. Next, I'd like to introduce Mark Monroe. Mark is a principal engineer in Microsoft's Data Center Advanced Development Group, working on future systems for energy, water conservation, and automation. He's a Six Sigma Master Black Belt with a focus on change acceleration in corporate settings. Mark led industry consortium, including Infrastructure Masons and the Green Grid, and served on the board of directors for the Center for Resource Conservation in Boulder, Colorado. He has a Master's of Science in Mechanical Engineering from Virginia Tech. Mark, take it away.
Thanks, Aaron. I'll also show some slides. Let's see. So we'll try this and say share, and we'll go into presentation mode. So hopefully you all can see what I'm going to talk about is how we see in Microsoft the use of hydrogen and what we call hyperscale. So for those of you that aren't familiar with the term hyperscale, let me define it a little bit. A couple of years ago, Satya Nadella, our CEO, talked about the amount of storage that would be required in the internet. And what he said was that this was an internal conference of software developers, was he said that we'll be going to 175 zettabytes of data by 2025. Up from about 40 zettabytes of data today. And if those of you that don't know your gigabytes from your zettabytes, there's a little guide over there on the right-hand side of the slide. So we're talking about billions of terabytes, trillions of gigabytes of data that are going to be part of the internet over that time period. And there's a product, or there was a product a couple of years ago made by EMC, Dell EMC, that was about 1 petabyte of storage. Took one computer room rack, took up about 22 square feet or about 2 square meters on a data center floor, used about 17 kilowatts of power. And what turns out then is that Satya said we're going to need 135 million of these racks, which would take up 105 square miles and use about 2.3 gigawatts of power. So I laid out a 10-mile by 10-mile square over Richland. And we have to fill this entire space with these 1 petabyte storage units. That's just storage. Oh, and by the way, hope you won't mind the 2 nuclear power plants that it'll take to power this stuff. So that's an idea of what data center scale is like, hyperscale is like when we talk about it. Another example real quickly about speed in the hyperscale industry. We have a saying that internet years are like dog years. There are 7 for every regular one. So in Quincy, Washington, sort of central Washington, we have a site that has some data centers. This was a photograph, an aerial photograph of it when I visited the site in late 2018, early 2019. There were, each of these buildings contains about 8 megawatts of computers and storage devices, networking devices that are used for the cloud. So you're looking at 1, 2, 3, 4, 5, 6, 7, 8. That's 64 megabytes of capacity, of IT capacity. And if we go to the latest maps on Bing, you'll see that there's now twice as many buildings on site. These are the original 2 that we were looking at. There's 3 more that are built. Actually, there's a 4th that doesn't show up on this picture, and there's a 5th and a 6th building that are currently under construction. So in 4 years, we've more than tripled the capacity that's happening in Eastern Washington. I'll give one more quick example. Boynton is a town in Southern Virginia near the Virginia-North Carolina border. And if you look, the kind of light yellow outline is the town of Boynton. The darker yellow are the pieces of land that Microsoft has purchased that we intend on building data centers on. And so we are building huge scale, and it's driven by demand. We're not doing this, for our own good. We're always driven by demand. There's constant demand for this digital infrastructure. And so let's talk then about the proton exchange membrane fuel cells that we've talked about, or where we've started to use these for backup power. And Ronan, apologies, my picture has a cat sign on it, but hopefully you aren't too put off. But generators, whether they're from CAT or from Cummins or from other suppliers, are critical to the electrical infrastructure that's required for the availability of the internet. The problem is that diesels are noisy, they're polluting, everybody uses them, but nobody really likes them around there. And we typically have to have fuel for 24 to 48 hours of backup power available on site in storage, and then we'll replenish from there. In 2018, we saw a demonstration at the National Renewable Energy Lab that had been put together with our consultation, equipment from Hewlett-Packard and Daimler, and integrated by a company called Power Innovations. This was a 65 kilowatt Daimler fuel cell running one rack of equipment. And it was a basic functional demo. It said, yep, we can start the fuel cell, the batteries will take over for a short time. We can use the fuel cell as the primary power source. It'll react to the load shifts that happen with computers, and it'll work just fine. Well, we said we've got to scale that up. And so in June of 2020, we demonstrated what I call a row of computers, about a 250 kilowatt system using 4 Daimler fuel cells. This was tested successfully, and I'll just kind of flip through some pictures. This is the actual unit, the 1, 2, 3, 4 fuel cells. The center contains hydrogen distribution and some control electronics. The control was mostly software driven on the lower right-hand side. This was the room where the fuel cell generator is back here. A lot of the support staff. This was the row of computers that we ran. Not every one of them is a computer, but they act like a computer for an electrical system. They have capacitive load, they have inductive load, they have resistive load. So the electrical system gets exercised. As you know, water vapor is the only product of the PEM fuel cells. And here's an animated GIF that shows, we could put our hand in it. It was about 50 degrees C or 110 degrees Fahrenheit coming out of the exhaust. You could walk through it. The hydrogen storage that we used in this case was gaseous. We had 4 of these trailers. We had to do a live swap when we did long duration testing. We did verify things like startup time, reaction to load. We made sure that we actually ran this through the qualifications that we do for diesel generators, including a 24 and a 48-hour duration test. And then we published some information about this about 2 years ago in July of 2020. One of the things that we said during that article was that we were going to continue on because now we have a 250 kilowatt system. We need to get up to multiple megawatt systems, and we've been working on that development ever since. Here's a concept of a 3 megawatt fuel cell generator on the right compared to on the left, a typical 3 megawatt diesel generator that we might use at one of our data centers. And you can see that individually they take up a little bit more space, but we think we can accommodate this in the data center designs that we do around the world. And so we're continuing to move forward with a design like this. But we are also excited about the possibility of data centers participating in this kind of integrated hydrogen economy. We will need to store a lot of liquid hydrogen in order to be able to meet that 12 to 48 hours of backup time. And there's other things we might be able to do with that. Maybe we put some electrolyzers in so that we can do more firming of renewable energies, interact with the grid. Maybe we take the boil off and build vehicle refueling stations so that we participate in a local economy. Maybe we share with natural gas blended lines, and maybe build our storage tank a third larger than we need and participate with local hydrogen elements. So we're very interested in being integrated into this hydrogen economy, not just being a consumer of the hydrogen and for the backup systems. But as you can imagine, we talked about 12 to 48 hours. a typical size of a data center, or at least a module of a data center that an Amazon or a Microsoft or a Google or Baidu or Tencent or one of the hyperscalers might use is around 30 megawatts. And we're going to need 100 tons of hydrogen on site, ready to go in case there's an outage. And that's quite a bit. So we've been working with various folks, the industrial gas providers and the fuel cell providers, on how we might meet these storage requirements and what other purposes we might use it for as we go forward. So we're very encouraged by the idea of zero pollution power generation. Of course, if we do that, then we may not be able to use it for more than just backup power, but as I mentioned, for grid interaction and ultimately for primary power, if we meet the dollar per kilogram goals that the Department of Energy has put forward. So I'll leave it at that, and we can go to question and answers.
Fantastic. Thanks a lot, Mark. Very interesting. I'm glad to see the Quincy data center being highlighted. My hope is that we'll be utilizing that Cummins electrolyzer just up the river from Quincy to make some hydrogen, so you guys can use it for backup power. So
that'd be great.
Happens there. I want to kick us off with a question that's shamelessly geared towards my own self-interests. As somebody who focused on critical materials challenges, and also as someone who has, I've spent most of my career, the electrochemical space I've been involved in has primarily been battery materials, and we've seen the battery industry just, growing explosively here over the last decade or so. Electric vehicle adoption is approaching 10% now, so we're talking about really, really high volume. And the challenge that they're seeing in the battery space is they did not do an adequate job of focusing on the supply chain ahead of that massive growth. And so now we're kind of retroactively going back and looking and saying, wow, we've relied too much on cobalt and the supply chain is not robust. We've got, all kinds of folks focusing on how do we avoid sourcing cobalt from the Democratic Republic of the Congo, where most of it comes from, and Chinese supply chains and things of that sort. So it's a big, big challenge. And what I'd like to help make sure that the hydrogen economy anticipates some of those same challenges, because it'll be the same thing all over again. All of the platinum group metals are in short supply. And so I'm very curious from each of the speakers, what emphasis, if any, your companies and your organization has put on addressing those critical materials challenges, trying to come up with technical solutions that minimize the use of those critical materials, enable recycling of those materials, do things to use earth abundance solutions or different kinds of catalysts. So I wonder if you could comment on some of those. And this is an area that I think is ripe for research. I know there's a lot of folks that I know of just within Washington State that are putting some emphasis on those catalysts. Would each of you mind commenting briefly on that, and then we'll get into some other Q&A.
Sure. So I can start from a Cummins perspective. Cummins is really, really strong on supply chain, right? So there is a lot of emphasis on, do we have the right supply chain? Do we have the right quality? Do we know how to get the material? And you're right on the battery side, right? I think the battery, and I've been in that space about 4 years ago, and there was also always this question on how would the adoption look like, right? And especially on the commercial vehicle, we always had this notion, are batteries really going to happen in commercial space or not? On the heavy duty side, and it just runs so fast that I think all of the prediction actually materialized, and it surprised everyone, because there was a little bit of pessimism on, is it really going to happen? And it happened fast. So I think that we have a lesson learned, right, from batteries, and moving into hydrogen, we are looking at it. In Cummins specifically, we are very focused on what we call remanufacturing, right? So we're using whatever components we can from the product that we have. So when we do the design, during the design phase, we are considering all of these things to see how can we develop a product that we can reuse a lot of the material back. And so it's all being considered from phase 0. How would it end up? Would we be in a different solution? You know, the demand picks up like the battery side. I don't know. I don't even know if there is a easy solution, but definitely research, use of new materials, seeing how can we reduce the materials that are hard to get is very, very important.
Fantastic. Thanks, Ronan. Max or Mark, would you care to comment?
Yeah, sure. So from the Ballard perspective, we are obviously aware, we have been since day one, about the issues related to utilizing platinum and other precious metals in fuel cells. So here there are three aspects that we consider. First is to reduce to the bare minimum the amount of PGM, of precious metals, of platinum in the MEAs. So we want to put only what is really needed, and that's why I was kind of mentioning in one of the slides that we really want to be able to identify in a very accurate way that what specifications we want to we put on our MEA designs. So we want to really be on target on reducing the cost without sacrificing performance and reliability of the product eventually. There is also a lot. So point one, emphasis on reduction of the PGM use and optimization. Point two, recycling and being partnering for the supply of catalyst in such a way that we are resilient to changes in price of platinum. This is another aspect. So there is a lot of focus currently on trying to understand what is the most efficient way of recycling, because of course recycling is possible and it can be done by refurbishing stacks and so on, but it's not a 100% efficient process. So there is focus now on doing that. And so this was the second aspect, if you want, related to being more resilient to the use of PGM, of precious metals. And lastly, it's to be open to research with new materials, for example, these non-PGM catalysts that have been studied and researched already for a number of years. And again, going back to the slide that was shown, the emphasis here is to be able to characterize this material properly, to understand how they behave, and to have a way of introducing them in a very fast way into our products.
And Aaron, I'll just say quickly, as a potential consumer of these things, we'll rely on our vendors then to develop those supply chain strategies. We're always interested in hearing about the new research and then pushing, the folks to be able to use them as quickly as possible. Rare earth metals obviously have a special place in every supply chain, and we want to be careful to make sure that we get no conflict materials of any kind.
Yeah, absolutely. And Mark, I'll just, I've actually, since batteries is my home space, I've actually talked a fair amount with the battery experts over there at Microsoft, and they've done a big audit. They've gone out and looked for all of the cobalt and things like that. So it's
we're very careful. We got good process. And try to make sure that we don't get into those situations.
It's encouraging to see that kind of leadership from companies like Microsoft. Max, there's a follow-up question here from the audience. They're curious about how widespread platinum recycling is from MEAs. Are there companies that are currently doing that? Yes. So catalyst suppliers, they are also active in recycling precious metals. There is a history behind that. Recycling was already happening for the three-way catalyst used in internal combustion engines. But I would say the level of recycling, the overall efficiency was not yet, or is not yet to the levels that we would need in the future for a widespread use of fuel cells. Yep, that's the challenge with all of this is scaling it appropriately, and as we produce, as we get to that, that hyperscale that Mark was talking about. Another question for you, Mark. If you want to use electrolyzers for renewable firming as well, I assume this can happen only till the hydrogen tanks are filled up. To do renewable firming, would you need fuel cell systems as well? The issue with that is that the fuel cell generation can be done only if the hydrogen tanks are close to being full to ensure 48-hour backup is available at 30 megawatts in this example.
Yeah, it's a great question. I think it all comes down to sizing and actual loads. And so we will size our fuel tanks so that we'd be able to produce 12, 24, 48 hours, whatever the requirement is, at full load, at 100% utilized systems and things like that. The reality about cloud computing is that it's almost impossible to get 100% utilization for that long of a period. Load varies by business day, by type of application, and we aggregate all that stuff together. We're rarely at full load. And so there'll be a portion of the fuel that would be available for that kind of interaction. Yes, we'd be only able to make hydrogen until the tank was full, but then we'd probably be able to use hydrogen, take some of the load, curtail some of our load from the grid if it was cost effective, or one of those other sharing techniques that I mentioned. We might have a partnership with a natural gas blending solution or vehicle fueling or other applications that might use some of that excess fuel.
Excellent, thank you. I have another question here from, let's see, it's provided that we, and this is not directed at any particular speaker, so anybody be happy to comment on it. Provided we address materials and supply chain issues, do you think that the demand for electrochemical systems is increasing proportionally to the renewable energy production and grid capacity? And if not, what will be the limiting factor, the grid capacity of the renewable energy production?
I'll say first, I don't think that hydrogen availability and is rising for the electrochemical systems, as mentioned, is rising proportionally yet. I think the renewables have at least a decade head start out of the gate and are really hitting their stride now in terms of cost and projects that are making them available. If we're to believe the things like the hydrogen shot from DOE, we may see the same kind of acceleration and demand come out of the hydrogen industry within a decade. But today, in 2022, it's not quite there. I think that all the speakers are anticipating that hydrogen demand will grow, and so will the marketplace over time.
Yeah, I'll just comment briefly on, I've spoken with a number of folks at Pacific Northwest National Lab about this, particularly as we address this challenge, because essentially what we're trying to do is eliminate fossil fuels from the entire mix, right? And so that's a huge portion of our energy makeup right now. If you're going to do that and replace all of that energy with electricity, we're talking about a 3-4-fold, maybe even a 5-fold increase in the power grid in terms of generation capacity. So it's a big challenge. We'll be needing to get all of that from renewables, and we're going to need to have fuels like hydrogen, to store all of that. I've heard from folks operating data centers, for example, that they've given that kind of power grid challenge, there might be instances where you would rather just deploy a power grid, or a data center that's not even connected to the grid, deploy the renewable assets, have enough backup power, enough hydrogen or other sustainable fuels on site to power the whole thing and not worry about the grid. So there's going to be a lot of challenges, a lot of differences in the way we move forward here with the energy supply. So we have a few other questions that have been answered in the Q&A, but I might go ahead and touch on some of those here, so that for the benefit of the audience, and maybe we can expand on them. Here's a question for Ronan. Can you briefly talk about the solid oxide fuel cell development at Cummins? What application, what size, what power, and what fuel?
So that's the question I'm unprepared to, Aaron. So sorry for that. I'm not that familiar with the SOFC product line, so I'll have to skip on this one. But if anyone is really interested, reach out to me, and I can always reach out to my colleagues and get responses.
I meant to read the question right below it, and I
No, no worries. That's okay.
Cummins uses alkaline and PEM electrolyzers. At what criterion is used to select which plant will have which technologies?
Yeah. So, I think this is where I probably give a generic answer, right? It depends, and it depends on the project and the customer needs. So maybe a bit differently from our fuel cell product line, which we try to go into a mass production product, right? Or not mass, but the high production volume, which we try to have a best fit. These are more project-based, right? So there are discussions in each facility with what are the needs and which technology would be better fitted and what power level and capacity they would need. And I don't know, maybe Mark, you have more insight from you as a customer on these things.
No, I mean, we still are feeling out how we'll end up using hydrogen overall, and so I think it remains to be seen how our interaction as the customer goes into that. Hydrogen is going to be one of a part of a portfolio of energy storage methods that we use in order to keep everyone's email flowing and gaming going and cat videos viewing and things like that. But so we're encouraged about the whole portfolio of those things.
All right, thanks, Mark. A question for both Max and Ronan, and something that I'm very interested in as well as we deploy these hydrogen assets is that what is the current cost in dollars per kilogram of the hydrogen produced for your electrolyzers?
I'm not sure I understand the question. We deal mostly with fuel cells, and the cost of hydrogen it's still on around $10 per kilogram. It's forecast to decrease, hopefully going down to $2 or maybe even less, depending on the locations and regions. I hope this answers the question.
Yeah, Ronan, would you care to comment?
Yeah, I don't know, again, if I have too much to add, but just like Max said, right, we know the prices today. Obviously, there are projections that the prices would go down. A lot of the customers are asking for TCOs that are equivalent to other products, right? So a truck customer with a diesel engine would come and say, hey, I want to have the same thing with my hydrogen truck, right? I want it to run for 1 million miles and be as cheap as a diesel engine, and that you guys can easily replace stacks just like you replace a cylinder block today or whatever, right? So obviously it all goes hand in hand, right? If the price of hydrogen goes down, we can bring a product that from a TCO perspective or total cost of ownership would be much better and much closer to these other products that they're used to. But it's like a chicken and an egg, right? As we have more products, all of the prices can go down together and improve the TCO. So again, I don't know if that answers exactly, like all of the numbers on hydrogen projections are coming from obviously external analysis and not Cummins's, but I hope that helped.
Yeah, and I'll just jump in to comment that it is actually very closely tied to the cost of electricity. That's your there's differences with different electrolyzer options in terms of efficiency and how they're utilized, but the cost of electricity is your primary raw ingredient there, in addition to water, of course. But we in the Pacific Northwest, we're starting to see hydrogen, substantially electrolytic hydrogen substantially lower than that $10 a kilo price point, down into this $6-7 a kilo, and people that are looking at deploying large-scale hydrogen production facilities in our region with our, hydropower assets and low-cost electricity. We're talking even in the $4 or $5 a kilo range, and it's exciting because that starts to become reasonably competitive with diesel at the current price points, and especially as we see that continue to evolve, we're hoping that some of those hydrogen earthshot goals can be achievable.
And I'll say also that we don't expect, we accept the cost differential of the pollution-free generator as an enabler. There are places where we can't build data centers anymore because either power grids are too congested or we can't get air quality permits for the big diesels that we need, even to run as emergency backup. And so if we need capacity in one of those areas, say the Bay Area of California, hydrogen might be the only solution that we have for long duration pollution-free backup systems that would enable us to build capacity there.
Yeah, no, for sure. We're getting close to time here, but I thought I would just point out one thing in particular that might be relevant for a lot of the audience, which is where we focus our R&D on going forward. A lot of the technologies have been developed. We're past the point where the fundamental research needs to be figured out. You guys are showing pictures of large scale development and deployment, and we're talking about going even bigger. And so as we go through this, getting into out of the fundamental research and into the pilot scale demonstration and full scale commercialization, what are the research needs that you would identify and the things where you need help from the research community to further advance this technology and make sure that it is successful in commercial deployment?
So maybe I'll go first here. The first area where we would benefit is in the advanced characterization techniques and fundamental understanding of the existing designs that allow us to have higher reliability and to maintain reliability of our products. This would be one aspect. For academic and collaborations, and also collaborations with national labs would be also relevant to again have opportunity to focus on areas where we don't really have the time or maybe even the budget to focus deeply. I'm referring specifically to maybe some high risk and high reward research activities on materials and like mentioned earlier, the non-PGM catalysts, and also maybe on new ideas for components, again, where we don't have maybe the bandwidth to do the research solo. Otherwise, we would have done it, as it was mentioned earlier on. So these are pretty much the two areas where I see most of the potential.
Yeah, and I don't know where to begin. Obviously, like we cannot conquer everything and we cannot do everything ourselves, right? So at Cummins, we really think that collaboration is the way to go, right? And we need to pick our battles and get help from wherever we can, and academia is definitely one. I definitely agree with Max. All of the characterization and life degradation and model building, that's definitely something that can help. I can also say that as power density grows up, it's really hard to keep up with all of the testing requirements, facilities, the additional power needs. So if academia could have places that we could leverage, and instead of us building and spending everything ourselves, split it with others, that would be very helpful as well. I know that the power density just keeps on adding up, and each new generation, it demands so much more infrastructure, I would say, to be able to develop and test that it's becoming harder. So maybe these are the two. And one thing which is really, really important, right? Help with commercialization. So sometimes it's relatively easy to develop a prototype or two, but how do we take it to scale? So that's another place that definitely I think collaboration and academia can help us with.
I'd echo that, Ronan. The commercialization is key. We've got to be able to, Microsoft doesn't want to be a fuel cell company. We want to buy a fuel cell from a supplier like Ballard or Cummins. The other area that I'll add to the research topics is hydrogen safety. Pretty well understood, but not necessarily in these newer applications. You know, when we went out and started talking to people about using hydrogen as emergency backup power, no one really thought about filling up a hydrogen tank, a cryogenic hydrogen tank, and leaving it there for nearly a whole year until you use a little bit of it for a 4-hour grid outage, for example. And so, you know, we need to understand very large storage tanks and the safety protocols that go around them, and how that will happen with regulatory bodies, AHJs, you know, as we try to build some of these things out around the world.
Fantastic. Well, thanks so much to all the speakers today, and thanks to the organizers. A really enjoyable panel discussion, and appreciate all the interaction. I'll hand it back to you, Shannon.
Great. Thank you, everybody. Thanks to Aaron and Olga for moderating, and Yuyan for putting everyone together with the panelists. I do want to close out today's event and let everyone know that the event is being recorded and will be available on the ECS YouTube channel, and then probably in about a week or so. But I also wanted to highlight some upcoming webinars that the Society has. So we know that the webinar series is a really great way to get engaged and involved, and showcases some distinguished speakers like we've had today between our panelists and our moderators. The next webinar that we have is scheduled for August 3rd with Dr. Judy Divarajan, characterization of lithium-ion battery thermal runaway in ESSs and EVs. And then the Pacific Northwest section has another webinar scheduled on August 17th with Dr. Yuyan Shao on conjugated metal, organic nanostructure synthesis, and electrochemical applications. You can always check our webinar schedule at electrochem.org/webinars. And if you're interested in presenting or have a webinar topic, please feel free to email it to me at shannon.reed@electrochem.org. And with that, again, a really big thank you to everyone, all of the panelists, moderators, and Yuyan for organizing today's event. And thank you to the audience for joining today. The webinar is now over.